Okay, so as I was saying, I incorrectly posted the wrong test number 2 in Canvas. I made a change this morning, so I apologize for that. And as a result, I've extended the deadline to, I think, Saturday, if I'm not mistaken, right? So please make a note of that. So with that said, let me now move on to answering this question. And this question gives you the enthalpy of formation of methyl alcohols, which is this right here. And the question is asking for you to calculate the Kc for this reaction. So there's a formula that we were introduced to earlier, yesterday in fact, which gives you the relationship between the free energy of a reaction and the Kc. Now, before we do that, we need to find the free energy of this reaction right here, because this question gives us the free energy of the formation of methanol. Turn this on here. Okay, so basically the free energy of formation or of the reaction is equal to the value for methanol, which is given here as minus 166.27 kilojoules. And then for the reactants, we have carbon, hydrogen, and oxygen. All of them are elements by themselves, and all of them will have a value of 0 in each case, right? So therefore, the answer here will be minus 166.27 kilojoules, all right? Now, if you remember the equation I showed you, it was delta G for the reaction is equal to minus RT, L, and K. What the question is asking for, or Kc, what the question is asking for is Kc. So if delta G is equal to minus RT, L, and Kc, then based on this, what would Kc be equal to? Anybody?
The delta G divided by minus RT.
Well, you're partially right. If you were to take this in steps, this would imply that L and Kc would be equal to minus delta G over RT. But what the question is asking for is Kc. So if L and Kc is equal to minus delta G over RT, then what is Kc equal to?
You would divide the natural log.
Nope.
Log.
Well, we have the log here already, the actual log here already. So if L and Kc is equal to minus delta G over RT, then what is Kc equal to? Yes, sir.
B.
E to the?
E over RT.
E to the minus delta G over RT, right? So basically, all we have to do is plug the numbers in. E to the minus 166.27 kilojoules. Now, the thing about this is, because we have kilojoules here, and R is expressed in joules per mole Kelvin. In fact, the actual value of R is 8.31 joules per mole Kelvin. What we have to do is some unit conversion. So we would convert, in this case, the kilojoules to joules. So we multiply by 1,000 joules above, 1 kilojoule below, and then we multiply by, or divide, I should say, by R, which is 8.31 joules per mole Kelvin, multiplied by the temperature, which is 25 degrees Celsius, which is the same thing as 298 Kelvin, all right? So when I do the number crunching, Okay, so the answer I got here is. All right, let me do this in part. Let me do this in steps. So I'm going to work out this part here first. 166.27 times 1,000 divided by 8.31 divided by 298. And I got, when rounded off to 3 sig figs, I got e to the 67.1. And then now, because this is one decimal place, when you work out this part here, okay, where's that function? So 67.1 raised to the e. I got 1.38, but you have to round it off to 1 sig fig because you have one decimal place here. So I got 1 times 10 to the 29 as the final answer. All right. Okay, any questions about this? Yes, sir.
Why is it 1 times 10?
Because the 67.1 here, that's one decimal place. Right? So if you're going from the e to the whatever the value is, whatever the number of decimal places here, the number of sig figs must be the same. Right? Because remember, doing the reverse, right? If you're finding the log of a number and you get your calculator results, whatever the number of sig figs in the number that you're finding the log of, number of decimal places have to be the same. So we're doing the flip side of that. All right? Okay, any other questions about this example? Any other questions? Any other questions? Any other questions out there in Zoom? Okay, let me clear this. And let me scroll down to question number 7. So number 7 says, consider the formation of NO from its elements, and it gives the equation. Use the free energy data provided to calculate Kp, all right? Now, in this case here, we have to find the free energy value. You'd have to go to the tables. In the interest of time, I'm just going to show you what the values are. So basically, for the free energy change of the reaction, that will be equal to 2 times the free energy of NO. When I looked it up, that was 86.55 kilojoules. And then I'll subtract from that the values for nitrogen and oxygen, which would be 0 and 0, right? So therefore, the answer is going to be 2 times 86.55, which works out to be 173.1 kilojoules, all right? So that's delta G for the reaction. But what the question is asking for is Kc. So how would we get Kc? How would we get Kc? Yes, sir.
E to the negative delta G over 1.
Again, we have to convert the kilojoules to joules. So we multiply this by 1,000 joules over 1 kilojoules. And then we divide all of that by, as you said, R, which is in joules per mole, Kelvin, times T, which is again 298 Kelvin. So let's see what that gives. 173.1 negative times 1,000, and then divide that by 8.31 times 298. Okay, so when I did that, I got e to the minus 69, how many sig figs? 69.9. So again, whatever the number of decimal places here, the number of sig figs have to be the same. So let's see what that gives. So 69.9 negative, shift that. Okay, so according to my calculation, this works out to be 4 times 10 to the minus 31. And that's how that is done. All right. Any questions about this one? Any questions? Okay, so that's the A part. Now the B part, clear this, is asking for Okay, so the B part it says, assuming that delta H reaction and delta S reaction are nearly constant with temperature, calculate delta G of the reaction at 700 degrees and then estimate the Kp from the new value of delta G, all right? Now, basically, let me just briefly describe the approach that we're gonna take. Okay, so basically what we need to do first is to find delta G of the reaction based on the delta H value and the delta S value. So remember, delta H is equal to delta G is equal to delta H minus T delta S. And we're assuming, of course, that all the values of entropy, enthalpy are standard, right? So what we have to do, and then after that, based on the delta G for this reaction, we find the Kp, which would be equal to e to the minus delta G reaction over RT, all right? So basically what we have to do is consult, I'm sorry, yes, sir.
7A didn't ask about KP.
I'm sorry?
For 7A wasn't asking about KP.
Yeah. For 7A. Yeah, and by the way, Kp and Kc are the same in this case, right? So yes, you're right. Kp is what the question is asking for, but the value of Kp and Kc are the same, right? Because the reaction is equimolar, right? In equimolar reactions, Kp and Kc values are the same. So, okay, so let me scroll back down to here. So, as I was saying, what we have to do is consult the tables. We look up the values or we calculate based on the table values, the delta H for the reaction, the delta S for the reaction. We plug them into this equation to get delta G, and then that value we plug into this equation to get the Kp, all right? So let's start off by finding the delta H of the reaction. So delta H of the reaction will be equal to the sum of the enthalpy of the products, which would be 2 times 90.25. So we'd have to look up the value for the enthalpy of formation of the NO, kilojoules per mole, minus 0 plus 0, again, right? And according to my calculations, this works out to be, so let me just be clear, I probably should include this here. This is for the NO, this is for the N2, and this is for the O2, right? So the reason why I multiply by 2 here is because in the original equation, let me squeeze this in right here. You have a coefficient of 2. Oh, wait a minute, it's the other way around. It's N2 plus O2, N2 plus O2 to give NO, 2NO, all right? So because you have a coefficient of 2 here, we multiply the value of the enthalpy of formation of NO by 2. N2 and O2, again, elements by themselves, so therefore those values will be equal to 0. And when you work this out, according to my calculations, I got 180.5 kilojoules, all right? So that's the delta H of the reaction, which is this part right here. Then we need to find the delta S of the reaction for the entropy, right? So again, you have to consult the tables, and I did that, and this is what I got. In the case of the NO, it would be 2 times 210.76 joules per mole Kelvin minus T, what's a T? 700 degrees Celsius. No, I'm sorry. I'm confusing it. It's the products minus reactants. So when you go to the table, you see that for the reactants, the value here is 191.61 kilojoules. Joules per mole Kelvin. I'm confusing the units too. Plus the value for the O2, which is 205.14 joules per mole Kelvin. So basically, this value here, or let me do it this way. This value here is for the NO. This value here is for the N2, and this value is for the O2, all right? So when I work this out, the answer I got is 24.7 joules per mole Kelvin. Okay, so now that we have delta S, which is this, and delta H, which is this, we can plug this, and the temperature into this equation to get delta G of the reaction. All right, so I'm going to need some space. So let me just erase this top part here. So delta G standard for the reaction will be equal to delta H, which is 180.5 kilojoules per mole. So this should be per mole. Minus T, which is 25 degrees, which is the same thing as 298 Kelvin, multiplied by delta S, which is 24.7 joules per mole Kelvin. And again, we have to do some unit conversion because we have joules here, we have kilojoules here. So what I'm going to do here is convert this joule to kilojoule. So I'm going to end up with 1 kilojoule above and 1,000 joules below. All right.
700 for the temperature.
Actually, you're right. We should use 700 for the temperature. Yes, 700 should go here.
Question.
Yeah.
Shouldn't the 24.7, shouldn't it have 2 decimal places?
24.77. So this should be 24.77 here. Okay, so yes, you're right about the Kelvin, the 700. Actually, it should be 700 plus 273 because they gave us the temperature in degrees Celsius. So 700 plus 273 gives 973 Kelvin. So 973 Kelvin would be the answer for this part right here. So let me erase this here. And let's work this out. So let me do the second part first, 973 times 24.77 divided by 1,000. And then I'll put a minus sign in front there. And then I'm going to add to that 180.5. And according to my calculation, this works out to be equal to 1. I have to round this off to 1 decimal place. So this would be equal to 156.4. 156.4 kilojoules. All right. So that's delta G. But we're not finished yet because we need to find KP or KC. Well, KP, I'm sorry. So let me erase this line here. And we're going to use the same equation as we used in the previous problems that we started today's class with. And that is delta G is equal to, KP is equal to minus delta G over RT, right? So minus delta G is minus 156.4. I forgot the E there. E to the minus 156.4 kilojoules divided by R, which is 8.31. Oh, firstly, I have to convert again from joules to kilojoules. So 1 kilojoule below, 1,000 joules above. Then we divide by 8.31 joules per mole Kelvin times the temperature, which is 973 Kelvin, which is 700 degrees Celsius. And let's see what that gives. So 156.4 divided by or multiplied by 1,000. And put a negative sign in front of that. Divided by 8.31 times 973. And according to my calculation, this works out to be, this part here works out to be minus 19.3. Again, it's one decimal place, which means that when I do the E function, so 19.3, negative sign, shift E, I got, I have to round this off to 1 sig fig, so the answer will be 4 times 10 to the minus 9. 4 times 10 to the minus 9. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? No questions? Okay, so that's basically it for this chapter. We've just done the last question in this assignment. So let me clear this here. And what I'm going to do is open up a Dropbox for this assignment right now before I forget. So assignments. This is assignment number 6. And today is the 24th. Let me see here. So I'm going to let it be due on Saturday. And the only reason why, what am I saying? Yes, on Saturday. Because your next test is going to be on the 31st. So I want to grade it and get it back to you so you can have that to review. Oh, shoot. I'm not finished with that yet. So let me go here. So, no. Available from today. Until Saturday. Okay, so that assignment number 6 is due this coming Saturday. All right, so with that said, we're going to move on to the next chapter, which is electrochemistry. And let me just say that the very first part of this chapter should be a bit of a review based on what you have done in M1. So let me get the PowerPoint up here. Electrochemistry, and as the name suggests, electrochemistry is basically looking at basically 2 types of reactions, where in one case, the chemical reaction produces electrical energy, and in another case, an electrical source will provide energy which drives a non-spontaneous reaction. So the first that I mentioned would be a spontaneous reaction that produces energy in the form of electrical energy. The other part would be non-spontaneous reactions that are driven by electrical energy being provided, all right? So that's what's stated here. That's what's stated right here, right? There are 2 electrochemical processes, as I mentioned before. What they both have in common is that they are both redox reactions, right? And I'm quite sure you have heard that term before. Redox, abbreviation for reduction and oxidation, right? So we're going to do a bit of a review of what a redox reaction is all about. Here's an example of a redox reaction, the reaction between magnesium and oxygen to form magnesium oxide, right? So you should recall that in the case of magnesium, it is undergoing oxidation because it is converted from magnesium atoms to magnesium ions as a result of the loss of electrons. So this would be the oxidation part of it, right? Oxidation involves loss of electrons. Yes, sir.
You upload the new slides for
Oh,
this.
all right. Yeah, let me do that. I thought I did, but so files, notes. And, okay. Okay, you should be able to have access to it now. Okay, so as I was saying, the magnesium is losing electrons and it forms a magnesium ion. So therefore we call this the oxidation half reaction. And then those electrons will be gained by the oxygen to form the oxide ions, and that would be the reduction half reaction. And when I teach Chem 1, when I teach this particular topic, to help students remember which is which, I would suggest that they use this mnemonic, oil rig. I don't know if you have seen this before. So this stands for oxidation involves loss of electrons, reduction involves gain of electrons. All right, so you might find that useful in terms of helping you to remember what is happening when something is being oxidized and something is being reduced. All right. So basically, this is what happens in every single redox reaction. Something is losing electrons, and those electrons are being transferred to something which would be undergoing reduction. All right. Okay. Okay, why is this thing? Okay, so just to review, we find the use of oxidation numbers very useful for telling whether or not a reaction is a redox reaction. And the definition of the oxidation number of an atom in or by itself or in a compound is given right here. It says the oxidation number is the charge the atom would have in a molecule or in an ionic compound if the electrons are completely transferred, right? And this is a tool, it's basically a measure of how oxidized an atom is. And we use it to say whether or not, if we look at the reaction and we look at the changes in the oxidation number, then we can tell whether or not a particular atom is being oxidized or reduced. So there are some rules, of course, which govern the oxidation numbers, how you can predict the oxidation number of a particular atom. And as I tell my students in Chem 1, you don't need to memorize these rules, but what you'll find is that when you continually use these rules, they become secondhand, all right? You just know them like that, right? So the first rule is that any elements that's not combined with anything and it's neutral, then basically the oxidation number of those elements will be 0, right? So if you have chlorine by itself, or if you have sodium by itself, or if you have lead by itself or cadmium, if it's by itself, not combined with anything else, then we can assume that the oxidation number of that element is 0, all right? The next rule, and here are some examples, some other examples right here, right? The next rule is that in the case of monatomic ions, like chloride, calcium, and so on, the charge on the monatomic ion would be the same as the oxidation number. And we have some examples right here. So for example, in the case of the lithium plus ion, the oxidation number is +1. In the case of the iron 3 ion, then the oxidation number is +3. In the case of the oxide ion, the oxidation number is -2. All right? Okay, next rule. And this rule is specific for oxygen, right? This rule says that the oxidation number of oxygen when it's combined with something else, and I probably should add that statement, that's kind of important. So let me squeeze that in. Let me put here, in their compounds. Make a note of that, right? In their compounds. So we're not talking about oxygen by itself. We're talking about oxygen combined with other elements, right? Okay, so when you have oxygen combined with other elements, the oxidation number of oxygen is usually -2, but there are exceptions. And the exceptions would be in the case of hydrogen peroxide or any compound containing the peroxide ion. And in those exceptions, the oxidation number of oxygen in those cases is going to be -1, all right? So in the vast majority of compounds, the oxidation number of oxygen when present in those compounds would be -2. But the exception would be in the case of hydrogen peroxide and anything that contains the peroxide ions. In those cases, the oxidation number of oxygen in those compounds will be -1, all right? So that's the rule, and that rule is, as I said before, very specific for oxygen. Okay, number 4, another specific rule, this time in relation to hydrogen, right? And again, I don't think I need to make any changes there. Okay, so in this particular rule, it says here that hydrogen, when combined, in fact, I need to add something here. So in their compounds again, right here. All right, So basically what this rule says is that the oxidation number of hydrogen, when you have hydrogen bonded to other elements, right? The oxidation number of hydrogen is usually +1. But the exception here is that if hydrogen is bonded to a metal in binary compounds, in those cases, the oxidation number of hydrogen is -1, right? So in most compounds, hydrogen, when present in those compounds, the oxidation number is +1. But if it is combined with a metal in a binary compound, then the oxidation number is -1. Let me see if I have any examples. Okay, so let me provide some examples here. I thought I had some here. So for example, if hydrogen is bonded to oxygen, in the case of water, right? The oxidation number of hydrogen would be equal to +1, all right? But if hydrogen is bonded to a metal like calcium hydride, hydride. Calcium hydride. The oxidation number of oxygen in this case would be -1, right? Because in the second case, you have hydrogen bonded to a metal, all right? Number 5, rule number 5 has to do with elements in group 1A. And again, I need to add in their compounds again, when they're combined with other elements. So this rule deals with elements in groups 1A, 2A, and fluorine, all right? So elements in group 1A, if they are combined with any other elements, their oxidation numbers will be +1, right? Elements in group 2A, when combined with other elements, their oxidation number is going to be +2. And fluorine is very unique. Fluorine in all their compounds have an oxidation number of -1, right? So there's no ambiguity as far as fluorine is concerned, right? So, for example, in the case of a group 1A metal example, if you have sodium chloride, that's a good example, right? The oxidation number of sodium would be equal to +1, right? In the case of a group 2 metal, where we saw, let me put this example down here, right? So the oxidation number of calcium is equal to +2, right? Because calcium is in group 2A. And then in the case of fluorine, it doesn't matter what compound it is. It could be sodium fluoride. The oxidation number of fluoride is equal to -1, right? When fluorine is bonded to any compound, it doesn't matter, right? The oxidation number of fluorine is -1, all right? Okay, the next rule has to do with situations where you cannot determine directly the oxidation number of a particular element based on the previous rules, right? So this rule will come in handy when it comes to that situation. And this rule says that the sum of the oxidation number of all the atoms in a molecule or ion is equal to the charge on the molecule or ion, right? So this rule becomes useful, for example, in this case right here. So let's say you're given this question and you're asked to determine the oxidation number of all the atoms in this particular structure, right? Well, based on the previous rule, in fact, based on rule number 4, we know that the oxidation number of hydrogen is +1, right? So we know that this is +1. And based on the rule before that, which I think is rule number 3, the oxidation number of oxygen is -2, right? So the question now becomes, what is the oxidation number of carbon? Because there are no rules that we have learned earlier which tells you directly what the oxidation number of carbon is. But because of this rule, we know that the sum of the oxidation numbers of hydrogen, carbon, and the 3 oxygens will give a value which is equal to the charge carried by the ion, right? So basically we can set it up this way. Oxygen is -2, hydrogen has an oxidation number of +1, and we don't know what carbon is directly, but we do know that when we add up all the oxidation numbers, oxygen, and please note we multiply by 3 here because we have a 3 down here, right? So that's 3 times -2 for the oxygen. For the hydrogen, it's +1, and for the carbon, we don't know what this is, right? So basically, we know that the sum of all of these will be equal to -1. So basically, it's just some simple algebra to find out what carbon is, and it turns out that carbon will have an oxidation number of 4, right? So basically, that's how you can determine the oxidation number of a particular element whose oxidation number cannot be directly determined by the previous rules, right? Basically, you just exploit the rule that says that the sum of the oxidation numbers of all the elements in a molecule or ion is equal to -1, all right? So that's basically how you determine the oxidation numbers of atoms in a compound or by itself, right? Now, that's important in terms of, or it's a useful tool, I should say, in terms of determining whether or not a reaction is a redox reaction. So for example, we're going to discuss balancing redox equations, which is something, again, you should have learned in Chem 1. But before we get to that, so let's say, for example, you're given Mg plus CuSO4 to form Mg2 plus, I'm sorry, to form MgSO4 plus Cu. So this is MgSO4 plus Cu, all right? So how can you tell that this is a redox reaction? Well, what you have to do is look at or look for any changes in the oxidation numbers of the particular elements as you go from reactants to products, right? So if you focus on the magnesium, for example, you see that the oxidation number of magnesium is 0 here, but over here it's +2, right? So that means that there's an increase in the oxidation number, right? So increase in oxidation number results in oxidation, right? On the other hand, in the case of the copper, when you focus on that, you see that copper here has a +2 charge. Over here, it has no charge. So there is a reduction in the oxidation number, reduction in your oxidation number, which means that this would be the copper 2+ is being reduced, all right? So that's basically how we can tell, based on the oxidation numbers, how we can tell whether or not something is being oxidized and whatever else is being reduced. And of course, you must have one with the other. You cannot have oxidation without reduction or vice versa. Another thing I want to point out, which will become important when it comes to discussing balancing redox equation, and that is that the number of electrons lost must be equal to the number of electrons gained, right? So we see that in this example, because as you go from magnesium with a 0 charge to the +2 charge, there is a loss of 2 electrons, And in the case of the copper 2+ undergoing reduction, there is a gain of 2 electrons, right? So in fact, what we could do, if we were to write down the net ionic equation for this reaction, we can write it this way: Mg to form Mg2+ plus 2 electrons, and then Cu2+ plus 2 electrons to form Cu, right? So basically, this would be your oxidation half equation, and this is going to be your reduction half equation. And again, you'll notice that the number of electrons lost in the oxidation process will be equal to the number of electrons gained in the reduction half equation. And this is true for every redox reaction without exception, right? Every redox reaction must have a situation where the number of electrons lost in the oxidation half reaction is equal to the number of electrons gained in the reduction half equation. And that will be true for the examples we're going to look at when it comes to balancing redox equations. So let me clear this. Yes, ma'am.
We know that copper was 2 + 2.
Well, you have to look at the formula right here, right? And you'll have access to the list of common ions, right? So you'll see that the sulfate ion has a -2 charge. So therefore, in order for the compound to be neutral, the copper must have a +2 charge, all right?
Why does the magnesium have a 0 charge?
By itself, right? If it's by itself, there's no charge, right? Okay, any other questions before we clear this? Okay, so let me erase this here. So let's talk about balancing redox reactions, right? Now, the best way, in my opinion, to do a problem like this, or to understand this, is to go straight into an example. And again, this is something that you should have met before in General Chemistry 1. So this should serve as a bit of review. Now, I will admit that this example here is kind of incomplete because I would not expect you to know what the other byproduct is, because this question says the oxidation of Fe2 plus to Fe3 plus by the dichromate ion. There's another product. So I'm just going to put here producing Cr3 plus. All right. So that would be the complete question. All right. So basically your task is to write down or figure out the balanced equation. So the steps I'm going to go through, in some textbooks, I think they call it the ion electron method. I remember seeing in one textbook, all right? Okay, so let me just show you how to do this. The first step is that you write down an unbalanced equation for this reaction, right? And that's straight from the information that's provided. So based on the information that's provided here, the Fe2 plus would be one of the reactants, the dichromate would be the other reactant, and the products would be Fe3 plus and Cr3 plus, right? So that would be the unbalanced equation that you're going to start off with. Okay, so that's the very first step when it comes to balancing an equation. Now, in some cases, they would give you this directly, right? In which case, you move on to the next step. And the next step is that you separate the unbalanced equation into two half equations, right? One half equation would be the oxidation half equation, and the other half equation would be the reduction half equation. So you separate it into the oxidation half equation, which is the Fe2 plus going to the Fe3 plus, and the reduction half equation, which is the dichromate going to the chromium 3 plus ion, all right? The next step is that we balance all atoms excepting oxygen and hydrogen. And we do this in the traditional way that we're accustomed to, right? Now, in the case of the first half equation, you don't need to make any changes because you have one iron on each side, right? So therefore, nothing needs to be done as far as that equation is concerned. However, when it comes to the second half equation, you'll notice that you have two chromium atoms here and you have only one represented on the right side. So what that means is that we need to put a 2 here to balance the chromiums, and therefore we end up with that as your result of doing that, right? So just remember, when it comes to the third step, to balance all atoms excepting oxygen and hydrogen by simply adding the appropriate coefficient in order to balance those atoms, all right? Okay, the next step is where we balance the oxygens, right? And I probably should have separated number 4 into 2 steps. So let me just explain how this works. For reactions in acids, it says you're going to add you're going to add water to balance the oxygen atoms, and you're going to add H plus to balance the hydrogen atom. So this is kind of like 2 steps in step number 4. So let's focus on balancing oxygen atoms, right? So basically, before, we never had this. We had this going to this, dichromate going to chromium, right? You'll notice that there's 7 oxygens here. So according to this rule, what you're going to do is you're going to add 7 water molecules on the right side, because by adding 7 water molecules on the right side, you are now balancing the oxygens, where you have 7 oxygens here balancing with the 7 oxygens on the left side, right? So that's basically how you balance the oxygens. Now, for the other half reaction, where you're going from Fe2 plus to Fe3 plus, there are no oxygens, so we don't need to balance any oxygens in that case, right? And then now we need to balance the hydrogen atoms by adding hydrogen ions. So what that means is that before, we had no hydrogen ions on this side. We have 14 hydrogen ions on the right side. So according to this rule, what we need to do is to add 14 hydrogen ions to the left side, and now all the hydrogens are balanced, all right? Again, in the case of the first equation, we don't need to do that, the iron 2 plus the iron 3 plus ion equation. We don't need to do that because there are no hydrogens present, all right? Okay, so now that we have balanced all atoms excepting oxygen and hydrogen, we balance the oxygen by adding water, we balance the hydrogen by adding H+. The next step, and this is a step where students tend to screw things up, the next step is to balance the charges, right? So in other words, what we need to do is to ensure that the number of charges on both sides are the same. So the question is, how do we balance the charges? We balance the charges by adding electrons to one side of the equation so as to achieve that charge balance, right? So how do we do that for this equation? Now remember, we had Fe2 plus going to Fe3 plus. If you notice here, we have a total of +2 charges here, and over here we have +3, right? So the question now becomes, to which side do we add electrons, and how many electrons do we add? And the answer is we add electrons to the right side, because by adding that 1 electron to the right side, we're adding a -1 charge. +3 minus 1 is equal to +2, and that balances with the +2 on this side. All right? So that's basically how we achieve the charge balance in the case of the first half equation. Now, in the case of the second half equation, this is the equation that we have at this stage, right? Again, just like we did here, we're going to look at the total charges on both sides. So here we have a total of 14 plus charges minus 2, so that gives us +12. On this side, we have +6 because the water has no charge, right? So therefore, the question now becomes, to which side do we add electrons and how many? And the answer would be that you'd add 6 electrons to this side, because by adding 6 electrons to this side, you're adding -6 charges total, and that will be equal to +6 on the left side, which is equal to +6 on the right side. So therefore, the answer is that you're going to end up with 6 electrons on the left side being added. So the mistake that students tend to make, especially when they're learning this for the first time, well, one of the mistakes is that they tend to add electrons on the wrong side, right? And to figure out which side you add electrons, it's very simple. You add the electrons to the side with the higher net charge, right? You add electrons to the side with the higher net charge. So like in the example that we just did, one side has a total of +12, the other side has a total of +6. So you're going to add 6 electrons to the side with the higher net charge of +12. And that reduces that total charge to +6, which is equal to +6 on the other side, all right? So please keep that in mind when you get to this stage, all right? Okay, so the next step now, which is referring to something I mentioned before, and that is that in all redox reactions, the number of electrons lost and gained must be the same. As we have it right now, that's not the case, because what we have here is that we have 1 electron here and we have 6 electrons here. They're obviously not equal. So basically the question now becomes, how do we achieve a situation where the number of electrons lost and gained are the same? Now, in this particular case, what you would do is multiply this equation here by 6, right? Now, you're going to multiply, as a result, everything here by 6, right? And I think I have the result of that here, right? So basically, when you multiply that equation by 6, you're going to end up with 6 electrons here, which would be equal to the 6 electrons that is in the other half equation. And then from here, the next step is you're going to add these 2 equations together, right? And of course, as we saw in previous problems on the different topics, whenever you add electrons, or I should say, whenever you add equations together, you're going to cancel out common items on both sides. In this particular case, the common item would be the 6 electrons. All the electrons must be canceled out in order for you to get the final answer, right? In some cases, in fact, we're going to look at some examples shortly where we're going to look at some cases where other items are canceled, namely water and hydrogen ions, but we're going to look at that later on. In this case, however, the electrons will cancel out and you add up what's left and you'll be left with, so this is the result of the addition of these 2. The 6 electrons will cancel out and you'll be left with the final answer, which is shown there, all right? And that would be the balance equation. What I normally recommend to my students when you get to this stage is that you do a final check through to make sure that everything is balanced, right? Which means that all the atoms are balanced and also all the charges are balanced, right? So let's look at this right now. We have 14 hydrogens on the left side. That balances with the 14 hydrogens on the right side. We have 2 chromiums on the left, 2 chromiums on the right. We have 7 oxygens on the left, 7 times 1 oxygens on the right. And then we have 6 ions on the left, 6 ions on the right. So all the atoms are balanced, but we have to make sure that the charges are balanced as well. So we add 14 plus charges to -2, and then we add that to 6 times +2. So that gives you 24 on this side. And then on the right side, we have 6 times 3, which is 18, plus 6, 24. So therefore, the charges are balanced as well. So therefore, we can be confident that this is the balanced equation. All right? So that's basically how you go through the steps in terms of balancing redox equations. All right? Any questions? Any questions? Okay, so let's have some fun with this. Before I forget, let me catch those persons who came in late in my registry here. Okay, is Barat here? Burke, not here. Gallegos, not here. Irvin, here. Kylie Medina, here. Rolando, not here. Ben Chapagata,
Yeah.
Weflen is here. And Wright is here. Okay. So what I'm going to do is go through some examples of balancing redox equations. So let me close this, get out to this. And let me open up a Word document so I can write on it. Okay, so I'm just going to make up an example. I don't know what the final answer is going to be. But let's say you're given MnO4 minus plus SO3 2 minus to give Mn2 plus SO4 2 minus. All right, I'm not even saying that this reaction will work in practice. This is just an exercise I've created so that you can understand how to do the steps. All right. Now, if you recall, when I went through the steps earlier, the first step is what?
You're gonna break the equation up into two parts.
Right, you're going to separate it into two half equations. So one half equation is going to be that. This would be the reduction actually. Right, and then the oxidation would be the other one. You give SO4 2 minus. Okay, very good. First step. What's the next step? Feel free to look in your notes. What's the next step?
Balance the atoms.
Balance all atoms excepting oxygen and hydrogen, right? Well, we don't need to worry about that in this case because you have one manganese on both sides here and we have one sulfur on both sides here. So we don't need to do that for this particular question. What's the next step? Again, feel free to look in your notes. What's the next step? And you guys out there in Zoom, you can chip in with your, oh, actually somebody did say something. Oh, that was Miss Weflin. Yes, I see you, Miss Weflin. I have noted your presence. Okay, yes, you guys out there in Zoom, please feel free to chip in as well. What's the next step? I'm sorry, yes.
We're gonna add H2O.
Okay, so you're going to, and the reason why you're adding H2O is to what?
To balance the
Exactly.
oxygen.
So let's look at the first half equation. To which side would you add the water molecules and how many? On the right side, how many? 4, exactly. Right? What about the second half equation? To which side would you add water molecules and how many would you add?
Left side.
How many? Exactly. Okay, very good. All right. So that's that step. You balance the oxygens by adding water as needed to the appropriate side. Okay. Next step. What's the next step?
Add electron.
Nope. You're jumping one step before we get to that. We add what?
The H plus
We add hydrogen ions. And why do we do that?
to balance the hydrogen.
Balance the hydrogen. Okay, so what does that mean for the first half equation? To which side would you add your H plus and how many?
We would add 8 to the left
Yeah,
side.
exactly. You add 8 hydrogen ions to the left side for the first half equation. And what about the second half equation? To which side would you add H plus and how many would you add? To the right side, how many? 2. Okay, very good. All right. So the next step is what you said earlier, balance the charges. So let's see if you can do this without screwing it up. All right. So now we have to ask ourselves the question, to which side would you add electrons and how many would you add? What do you look for in order for you to answer that question?
The charge.
You look for the total charges on either side, right? So let's look at the first half equation. How many total charges do we have on the left side? Nope. We have 8 plus charges minus 1. So that's plus 7 on this side, right? How many charges do we have total on the right side?
Just 2.
Plus 2, right? Okay, so the question is, to which side would you add electrons and how many? What did I say about adding electrons? You add electrons to which side? To the side with the? No, not lower, to the side with the higher net charge, right? So which side has a higher net charge? The left side, right? So how many electrons would you add in order to reduce plus 7 to plus 2? 5 electrons, exactly. So by adding 5 electrons, you're adding 5 negative charges to get that reduced to plus 2, which is equal to the plus 2 on the right side. Next step, or do the same thing for the second half equation. Again, the question is, how many electrons would you add, and well, to which side would you add and how many electrons? So what's the total charge in the case of the second half equation? What's the total charge on the left side? Minus 2. What's the total charge on the right side? No,
No, 0.
0. Okay. So the question is, you look puzzled
Is there 0 again?
because you have minus 2 and then you have plus 2,
Okay, yeah.
right? Okay. So again, to which side would you add electrons? Remember, you add electrons to the side with the higher net charge. So which side has a higher net charge in this case? Which one is higher, minus 2 or 0? 0, right? So that means you're going to add electrons to the right side. How many electrons would you add? Exactly. So we add 2 electrons so that this becomes minus 2, which balances with the minus 2 on that side. Okay, very good. So now that we have balanced all the atoms and all the charges, the next step, let me just erase this here, is that we need to do what? What's the next step? Now that we have balanced all the atoms and all the charges, the next step, feel free to look in your notes.
Number of electrons in both equations are equal.
Exactly, right? So how do we achieve that in this case? Because in this case, we have 5 electrons here in the reduction half equation, and we have 2 electrons here in the oxidation half equation. So how would you achieve the balance of the electrons?
Multiply top by 2, the bottom by 5.
Exactly. So multiplying this equation by 2. Now remember, you have to multiply everything by 2, right? So this would be 10 electrons plus 16 H plus, H plus 2 MnO4 minus. And then on the right side, you're going to have 2 Mn2 plus 8 H2O, right? And then as Mr. Medina suggested, we have to multiply that equation by 5. So when we do that for the second half equation, it's going to be 5 H2O plus 5 SO3, 2 minus, to give 5 SO4, 2 minus, plus 10 H plus 10 electrons. All right? And then we add them up. Now, the 10 electrons will cancel out, of course, right? That must always happen, right? If you have electrons left over, you did something wrong, all right? So all the electrons will cancel out, right? But there are other items in this case that will cancel out. For example, these 10 hydrogen ions will cancel out 10 of these, leaving behind 6. But you see that? And then not only that, these 5 water molecules will cancel out 5 of these, leaving behind 3. All right? So when we add everything together, we're going to end up with 6H plus 2MnO4 plus 5SO3 2 minus, and then on the right side, 2Mn2 plus 5SO4 2 minus plus 3H2O. All right? And then, as I always say, and I'm going to say it again, when you get to the final equation, you check to make sure that everything is balanced. So let's see if that is the case. In this case, we have 6 hydrogens on this side. We have 3 times 2, 6 hydrogens on the right side. So that's balanced. We have 2 manganese on this side. We have 2 manganese on the right side. So that's also balanced. In terms of the oxygens, we have 2 times 4, that's 8. 8 plus 15. So 8 plus 15 gives you what? That gives you 23. 5, 3, 15 plus 8. So that gives you 23. And then over here, we have 5, 4 is 20 plus 3, 23 oxygens. So the oxygens are balanced. And then we have 5 sulfurs here, 5 sulfurs here. So that's balanced. And then the charges. Let's see what the charges are on the left side. We have plus 6 for the 6 hydrogen ions, minus 2 manganate, and minus 10, right? So that's equal to what? 6 minus 2, that's plus 4. 4 minus 10, that's plus 6. And then on the product side, we have plus 4, 2 times plus 2, minus 10. So that gives you plus 6. So the charges are balanced as well. So we can be confident that this is the final answer. Is there a question?
Minus 6.
I'm sorry, minus 6. My bad. Yeah. Hold on. They should both be minus 6, actually. Yeah, minus 6, minus 6. Thank you. So that's how you do that. All right? Any questions about this? Any questions? Any questions? Okay, so let's go to the assignment. Let me hand these out to you guys. So this is assignment number 7. Take one of us down. And for you guys out there in Zoom, let me check to make sure I published that assignment. So this is assignment 7. Okay, so I did not publish it, so let me do so now. Okay, so you guys out there in Zoom should be able to access assignment number 7. Let me pull it up now. Okay. Now you'll notice it says here acidic solution. I'm going to talk about how things are different in a basic environment, but that's for later on. I want to make sure that you master this now so that, you know, when it gets to the basic situation, you'll have very little issues, all right? So this question is asking for you to balance the following redox reactions using the half reaction method. So the first one is this right here. So based on what we have covered so far, what would be the first step in this process? Okay, so what would be the half equation?
HCOO.
HCOOH
And then CO2.
to form CO2. Okay, and what's the other one?
O4.
MnO4 minus to form
Mn.
Mn2 plus. All right? Okay, what's the next step? Well,
Balancing oxygens and hydrogens.
right, well, actually, the next step is to balance all atoms excepting oxygen and hydrogen. But of course, in this case, we don't need to worry about that because we have one carbon here, one manganese here, one manganese here. So those atoms are already balanced, all right? So what you just said would be the next step, and that is the balance of oxygens and hydrogens. How would you balance the oxygens?
First one, I don't think you have to.
Exactly, because you have two oxygens here, so you don't need to do anything as far as that is concerned. What about the second half equation?
Second one, you add, 4, right?
Got 4 water molecules on the right side. Very good. Okay, the next step is, yes, ma'am.
There's 2 hydrogens, but you don't have to balance those.
Yeah, that's what we're talking about now, the next step. What we did not have to do is balance the carbons. And we did not need to balance the oxygens because we have 2 oxygens on either side already. So the next step is to balance the hydrogens, right? So, since you spoke up,
And 2H to the right.
exactly, you had 2 hydrogens on the right. What about the second half equation? How do we balance the hydrogens in the second half equation? You had 8 hydrogen ions on the left. Okay, very good. So again, next step is where we balance what?
The charges.
All right, so let's see if you can do this on your own without messing it up. For the first half equation, to which side would you add electrons and how many? Two electrons on the
On the right.
what's that?
Why would it be on the right?
Okay, remember what I said. You add electrons to the side with the net higher charge. So the left side has 0, the right side has +2. So you'd add 2 electrons on the right side. Okay, what about the second half equation? To which side would you add electrons and how many would you add?
Left side.
How many? Exactly. +5. Okay, very good. Next step.
Get an equal amount of electrons.
Okay, very good. So how would we achieve that?
This first one times 5
Okay, multiply this one by 5 and this one by
times 2.
2, exactly. So when you multiply this by 5, you're going to get 5HCOOH to give 5 CO2 plus 10 hydrogen ions plus 10 electrons, right? And then for this one, it's multiplied by 2. So that would be 10 electrons plus 16 hydrogen ions plus 2 MnO4 minus. And then on the right side, you're going to have 2 Mn2 plus 8 H2O. All right? What's the next step?
Add them together,
Add them together. Okay, what will cancel out?
the electrons.
Electrons must cancel out, as I said before. But are there any other possibilities in terms of things canceling out?
The hydrogen ion,
Right. So-
which,
So what?
so the 10 hydrogen ion would cancel out, and then there would be 6 left.
Very good. So, and I don't think there's anything else to cancel, so we just write down what is left. 5HCOOH plus 6H plus 2 permanganate. And then on the right side, you're gonna have 5 CO2 plus 2 Mn2 plus 8 H2O. And again, what we do is check to make sure that everything is balanced, including the charges on both sides. So let's see if that's the case. So let's talk about the hydrogens first. So this is 5 times 10 hydrogens plus 6, so that's 16 hydrogens on the left side. And we have 16 hydrogens here, so the hydrogens are balanced. We have 5 carbons here, 5 carbons here, so the carbons are balanced. We have 5 times 2, 10 oxygens. 10 plus 2 times 4, that's 18 oxygens. Here we have 10 oxygens, 5 times 2 plus 8, 18, so the oxygens are balanced. And what else? The manganese, we have 2 here, so the manganese are balanced. And then now the charges, we have plus 6 here, minus 2, that gives plus 4. And we have 2 times plus 2 plus 4 on the right side. So now the charges are balanced. So therefore, that would be the correct equation. All right? Any questions? Any questions? Okay, let me clear this here. So let me see here. B part. Okay, now the B part is asking for basic solution. So what I'm going to do is okay, you know what? Let me go back to this here. Okay, I'm going to show you how to get to the basic solution based on the answer we got from this example that we did. So let me erase this here. All right, so this here, which we did earlier, would be the equation for this reaction in an acidic environment or medium, right? Now, how do we get from acidic to basic, right? The way we do that is that we look at the number of H plus ions on either side. It doesn't matter which side where it is, right? And what we do is we add the same number of hydroxide ions to both sides. So what we're going to do is add 6 hydroxide ions here, and whatever you do to this side, you have to do to this side, 6 OH minus ions, right? Now, what you need to recognize is that for every H plus that combines with an OH minus, will give a water molecule, right? So what that means for this is that the 6 H plus ions, when it combines with the 6 OH minus ions, gives 6 H2O molecules, right? And then what we can do next is recognize that because we have 3 water molecules on the right side, they can cancel out 3 water molecules on the left side, leaving behind 3 water molecules. So when we get to the final equation, it's going to be 3 H2O plus 2 MnO4 minus plus 5 SO4 2 minus. And then on the right side, you're going to have 2 Mn2 plus plus 5 SO4 2 minus plus 6 OH minus. And this would be the answer if the question is asking for the equation in a basic medium. All right? So basically, you do everything that we did when it comes to determining the equation in the acidic medium. And then, as I said here, whatever the number of H plus that you have on one side, you add the same number of hydroxide ions, and that will give you the same number of water molecules, right? And then if there are any water molecules on the other side, and by the way, you have to add the same number of hydroxide ions to both sides, right? And then if there are any water molecules to be canceled out, you cancel them out, as we did in this case. This 3 will cancel out 3 of these 6. So you're going to end up with 3 water molecules on this side and the rest of the equation, right? And that's basically how you get the basic the equation under basic conditions. All right? Yes, ma'am.
On the left side, how did we get the 3 again? Because
Or did we get?
you see how you crossed out 6 H2O? Then you put.
Well, we got the 3 from earlier. You mean this 3 here?
No, on the left side of,
Oh,
yeah, down.
yeah, we
where
go,
you're at.
okay, so before we had 6 water molecules here, and we have 3 on this side. So these 3 water molecules will cancel out 3 of the 6, leaving behind 3. Let me, okay,
I can't, yeah.
let me erase this here. Before, The 6H plus 6OH minus gives you 6 water molecules.
Mhm.
Here, we had, let me erase this here. We had 3 water molecules. Right?
Yes.
So what's gonna happen is that these 3 water molecules will cancel out 3 of these, leaving behind 3.
Okay,
You see what I'm saying?
yes.
So that's why you have 3 water molecules here. You have no water molecules left on the right side. All right? Okay, any other questions about this particular example? So if you understand this, let's see if you can do this. The B part. Well, B part is kind of different. Let me help you out as far as starting this is concerned. You'll notice that in the case of the B part, you're starting off with 1 reactant and you have 2 products, right? So the question now becomes, what would be the half equation that you start off with? And this is how you go about doing that. You're going to start off with HXeO4 minus, the form XeO64 minus, and then you're going to start off with the same reactant, HXeXeO4 minus, the form Xe, right? So, oh, by the way, this should be minus, right? So basically, you're starting with the same reactant. What's actually happening here is that some of the original reactant will be reduced and the rest will be oxidized, right? So you're going to start off with this here being the, you're going to start off with this one being the oxidation, half reaction, and this one will be the reduction, half reaction, all right? Okay, so after this, we go through the same steps as we did in the previous example. So what would be the next step in this particular case? Let me erase this here. What would you do in the next step?
So I thought it was the other way, that the oxidation was the bottom one and the reduction was the first one.
No. The reduction would be the bottom one. Because if you were to calculate the oxidation number of xenon here, +1 plus X minus 8 equals -1. So that's X minus 7 equals -1. So X would be equal to +7 minus 1, which would be equal to +6. So this will be +6. This will be 0. So that's reduction. And if you do a similar calculation, you'll see that the first one is oxidation. All right, so what's the first step in this? Since I've started it off for you guys, what would you do in the next step?
You would make sure that the xenon is balanced.
Okay, which it is, so that's, we don't need to do much work there. What would be the next step?
Hydrogen.
Oh, you're balancing what first? After balancing all the other atoms excepting hydrogen and oxygen, what's the next thing you balance?
The oxygen.
The oxygen, okay, very good. So how would you balance the oxygens for the first half equation? How many oxygens do we have on the left? 4. How many do we have on the right? So where would you add the oxygens and how many? 2 to the left, so 2 water molecules you're gonna add. Okay, what about the second half equation? To which side would you add the oxygens and how many would you add? 4 water molecules, exactly. Very good. Okay, what next? The next step would be to balance the. How would you do that? Let's focus on the first half equation. 5H plus on the right, all right? What about the second half equation?
7 on the left.
Exactly. Okay, next step. We have to balance the charges. How many charges total for the first half equation? How many charges total do we have on the left? -1. How many total do we have on the right?
One.
+1. So to which side would you add electrons and how many electrons would you add? Add 2 electrons on the right. All right, remember you add electrons to the side with the net higher charge. Okay, what about the second half equation? Let me erase this here to avoid confusion. Okay, what would you do to the second half equation? How many charges total do we have on the left? Hmm?
Six.
+6. You have 7 plus -1, right? And then how many total do we have on the right?
0.
0. Okay, very good. So to which side would you add electrons and how many would you add?
On the left side, we would add 6.
Exactly, 6 electrons. All right, next step. Now that we have balanced everything for each half equation, what's the next step?
We would multiply the top equation by 3,
Okay. And why do you want to do that?
so that we can cancel out the electrons.
Okay, you want the number of electrons lost equal to the number of electrons gained, right? So when we multiply the top equation by 3, you're gonna end up with 6 H2O plus 6 HXeO4 minus. Not 3, I'm sorry, not 6, 3, I'm sorry. And then on this side, you're gonna have 3 XeO64 minus plus 15 hydrogen ions plus 6 electrons. And as she correctly said, when you add this equation to this equation, you want to cancel out the electrons, right? Are there any other items that can be canceled out when you add these two equations? Okay, so these 4 water molecules will cancel out 4 of these, leaving behind 2. Anything else? Okay, these 7 hydrogen ions will cancel out 7 of these, leaving behind 8, right? And then we just simply write down what is left. Now, please note, we have this, which is the same thing as this on the same side, right? So we can simply represent the addition of those two as, oh, before I do that, let me put the 2 H2O first, right? But I was about to say that you can add this to this. You have 1 of these, you have 3 of these. So this would be 4 HXeO4 minus. And then on the product side, you're going to have Xe plus 3 XeO64 minus plus 8 H plus. All right. So at this stage, I would check to make sure everything is balanced. Let's see if that's the case. We have 4 plus 4, 8 hydrogens. We have 8 hydrogens here. We have 2 oxygens plus 4 times 4 is 16. So that's 18 oxygens. And here we have 3 times 6, 18 oxygens. We have 4 xenons. We have 3 plus 1, 4 xenons. And then as far as the charges are concerned, we have -4 total, 4 times -1. Here we have -12 plus 8, which is equal to -4. So the charges are balanced as well. So we're not finished yet because this that we have just completed is under acidic conditions. The question said specifically for you to determine the equation for basic conditions. So if you remember what I said earlier, what would we do to get the equation for the basic conditions? We had what? Okay, so how many hydroxide ions do we need to add? 8 to both sides, exactly. So we add 8 hydroxide ions to both sides, but in this case here, the hydroxides will combine with H plus to form 8 H2O. And over here, you're gonna have plus 8 OH minus, right? And then what?
You take the two H2Os and then subtract.
Cast over the 4, with the 8 to leave behind 6, not 4. So the final answer would be 4 HXeO4 minus plus 8 OH minus on the left side. And then on the right side, you're gonna have Xe plus 3 XeO6 4 minus plus 6 H2O. And that's it. And that should be your final answer. All right, any questions about this? Any questions? Okay, so what I'm gonna do is leave for you to do the rest of question 1. Let me see, question 1 goes from A to D. Okay. Actually, no, it goes to E. Goes to F. So you have a lot of G, H. Right, so A to H. So you have a lot of equations there to get your practice on. By the time you're through with those, you should be experts in balancing redox equations. All right? Okay, let me go back to the PowerPoint and see what next we can talk about in the time that we have left. Here it is. Okay, I'm just going to commence initiating this discussion and then stop for the day. All right, so as we said before, electrochemistry involves basically looking at the intersection between electrical energy being used up or being produced and the chemical reactions, right? So what we're looking at here is what is called a galvanic cell. It's a device that uses chemical reactions to generate an electric current. And what you're going to find is that these cells basically exploit redox reactions, all right? So let me just describe what we have here in this setup. We have 2 solutions in separate containers. One contains zinc sulfate on the left, the other one contains copper 2 sulfate on the right. We have a piece of zinc metal, which is dipped in the zinc sulfate solution on the left, and we have a piece of copper metal, which is dipped in the copper 2 sulfate solution on the right. And both metals are connected by an external circuit, which includes an instrument here, which if you have done any physics, you should be familiar with this. This is called a voltmeter. And what it does is that it measures what is called the potential difference between the 2 solutions on either side, right? So what you'll observe is that when you stick the metals into their respective solutions, the voltmeter will indicate that there's an electric current passing through, right? So the electric current is basically coming from, or the electrons flowing through the external wires will be coming from the zinc and will be basically reaching the copper right here. Now the question now becomes, where do these electrons come from and where they're going? Well, as far as where the electrons are coming from, they come from the oxidation of the zinc metal, and the half equation is shown here, right? So basically the zinc is undergoing oxidation by the loss of 2 electrons for each atom, and those electrons will enter the external circuit to form an electric current. And I should add, I don't know if you have met this if you have done physics before, basically an electric current is a flow of charge, right? So as far as what is happening in the external circuit, the electrons are basically, as a result or by virtue of the fact that they're moving through the external circuit, they're basically creating an electric current, right? So that's what's happening as far as where the electrons are coming from. Where the electrons are going to, Well, as I said before, they're going to the copper, but not only are they going to enter the metal right here, but the electrons will enter the metal and then leave the metal and add to the copper 2 plus ions in the aqueous solution here. And therefore, you're going to have a redox or a reduction reaction taking place where the copper 2 plus will give or gain 2 electrons to form the copper solid, all right? So basically what you're going to have is a redox reaction where one half reaction will take place in the zinc sulfate solution and the other half reaction will take place in the copper 2 solution. And therefore we can write down the net equation by simply adding this equation to this equation, and this would be the net equation right here, all right? So this is a spontaneous redox reaction, which basically means that the reaction is spontaneous. We know that what that means. It produces energy in the form of electrical energy, and the current that is produced enters the external circuit. Now, a couple of things I need to mention. Because the zinc is forming the zinc ions, if the reaction runs long enough, what you'll find is that the mass of the zinc will start being reduced, right? So if you weigh the zinc before, set up the experiment, run the current for a while, and then you weigh the zinc afterwards, the mass will decrease for the zinc. And the opposite will be true for the copper because, of course, copper is being produced, so therefore the mass of the copper would increase, all right? So that's the first thing. The second thing I need to make mention of is the fact that if you allow the reaction to proceed for a while, eventually what will happen is that you're going to have a buildup of zinc ions. So the zinc ion concentration is going to increase right here. And if it increases to a certain extent, to a certain level, then what's going to happen is that the current will stop, right? Because basically, you're trying to have more electrons being removed from something which has positive ions to begin with. So basically, the reaction will stop. And for the same reason, the copper 2 plus, what happens in the copper 2 plus solution is that there's going to be a buildup of the sulfate ion, right? There'll be, what's the word I'm looking for? Like, you're going to have more sulfate ions than copper 2 plus ions present in the solution, and that will cause the current to stop as well. Now, in order to prevent that from happening or reducing the likelihood of that happening, we have as a part of the apparatus what is known as the salt bridge. The salt bridge is basically, if I remember correctly, it's agar gel, which is soaked in a particular ionic compound solution. In this case, it would be soaked in potassium chloride solution. And basically the role of the salt bridge is to ensure that the current continues in the external circuit, for one, by making sure that the zinc ions are replaced by the chloride ions, and that maintains the neutrality of this solution here, right? And as far as the copper 2 plus ions being depleted here in this solution, the potassium ions will replace it, and therefore, again, maintain electrical neutrality, which allows the current to flow. So that is being explained right here in the next slide, right? Where it says here, for the cathode, the oxidation of the zinc leads to a buildup of zinc ions, and then the zinc ions will move into the salt bridge, and at the same time, the chloride ions will move into the solution. So therefore, the balance is maintained in that half of the setup. And then for the anode, basically there'll be a buildup or excess of sulfate ions. So what will happen is that the sulfate ions will move into the salt bridge, and the potassium ions will be leaving the salt bridge, entering into the solution, and again, maintaining neutrality so that the current will continue. Now, going back to the previous slide, I skipped over the nomenclature for the different solutions and the metals that are dipped in it. So we say that this combination right here, we call that the anode. And the anode is where oxidation takes place. So at anode, we have oxidation, right? And then the other half of the setup is called the cathode. So at cathode, we have reduction, all right? And this is true for all cells, including galvanic cells. We're going to learn later on about electrolytic cells, and it's the same thing. Reduction takes place at the cathode, oxidation takes place at the anode, all right? Okay, Okay, let's see what's on the next slide. So, we can measure what is called the potential difference between the cathode and the anode of any cell, right? Basically, we use an instrument known as a voltmeter, and here's a picture of one. So this is basically a situation where you have your copper in your copper 2 sulfate solution, your zinc in your zinc sulfate solution, and they're connected to the voltmeter, and you can see the readout right here. There are some different terminologies for the value that is measured here. You can call it the cell voltage or the electromotive force, which is a bit of a misnomer because that term electromotive force came from back in the day when they thought that there's a force that is actually pushing the electrons through the wires. We now know that not to be the case, but that term still lingers in our discussion. And then we have another term which is called the cell potential. So from time to time, you might hear me talk about cell potential versus cell voltage. They both mean the same thing. Another thing I want to talk about is a very shorthand way of representing what I showed you on the previous slide, the diagram that I showed you on the previous slide, and that's called a cell diagram. It's basically a shorthand way to show the composition of a cell. And again, going back to the example that we looked at, we saw that the actual net reaction is a zinc undergoing oxidation to form zinc 2 plus, and at the same time, the copper 2 plus is being reduced. So we can represent this with this, which is a cell diagram, right? So this part here, this the half on the left side represents the anode, which is made up of the zinc solid, and then you draw a line and then zinc ion, and then you have to put some information about what the concentration of the ion is in the aqueous solution. And then you have two lines to separate the anode from the cathode. On the right side, you have the cathode where reduction takes place, and you have the copper 2 plus. Again, you have to indicate the concentration of the copper 2 plus. Draw a line here and then copper. And you'll notice that the way, the order in which we write down the species is that we're indicating that over here, the zinc is converted to the zinc 2 plus, and over here, the Cu2 plus is converted to the copper. So this is where oxidation takes place, and this is where reduction occurs. All right? So that's just a shorthand way of representing the composition and the setup of the galvanic cell. Okay, I think I'm going to stop here for today, and we're going to continue our discussion on Monday. All right? So. Okay.